So today I will be speaking about the crystal field theory. So crystal field theory can be understood by the following ways. That first thing is it does not assume the overlap of orbitals on the metal ions. So it doesn't assume the overlap of the any orbitals of the metals with the ligands. Instead, it considers that the ligands will be placed around the metal ions. So now what do you mean by the ligands? We already studied that ligands are known as an electron donors. They donate the pair of electrons towards the metal ion. And here in CFT, the ligands are also considered as a negative point charges. So here, according to CFT, the ligands are also considered as a negative point charges. Examples you can consider often Cl minus, Cn minus, F minus, and etc. And here the ligands are not only considered as a negative point charges as if they are having the negative charges. Along with that, you can find the dipole molecules. Examples for the dipole molecules will be like H2O, NH3, etc. And here the negative ions in the dipole will be forming a bond or will be donating the pair of electrons to the metal ions. In H2O, an oxygen will be the negative, and in NH3, nitrogen will be the negative ion. So these negative ions in the dipole molecules will donate the pair of electrons. So next, we shall know about the crystal field in the octahedral geometry. Next, CFT in the octahedral geometry. And here the octahedral geometry will be considered to be the best in order to explain properly about the placement of the ligands over the metal ions. So here in the octahedral complex, what happens? Here a metal atom will be at the center and the ligands approaching will be on the axis. So in the octahedral complex, the ligands will approach the metal atom from on the axis. So here in the octahedral complex, we can find the degenerate orbitals. Degenerate orbital means which will be having the same energy. The orbitals which will be having the same energies will be known as an degenerate orbitals. So in the octahedral geometry, the d orbitals will be having the degeneracy. So the orbital lobes of d orbitals are dxy, dxz and dyz. And other two will be the dx square minus y square and dz square. So these are the orbital lobes of the d orbital. So when the ligand approach the metal atom on the axis, then these degenerative orbital will loses their degeneracy and they form as non-degenerate orbitals and they form as non-degenerate orbitals. So there is another theory in the CFT where when a ligand is approaching the orbital of the metal ion, there will be a repulsion between the orbitals of metal ion and the ligand. So there will be a repulsion between the orbital of the metal ion and the ligand. So due to this effect of the repulsion in the degenerate orbitals, the set of two degenerate orbitals, that will be dx square minus y square and dz square, will experience the higher repulsion and becomes a higher energy state, and the other three set of lobes of degenerate orbitals, that will be dxy, dyz and dzx. Here, other three set of the orbitals will experience the lower repulsion and moves to the lower energy state. And these set of two degenerate orbitals will be called as an EG orbital, and the set of three degenerate orbitals will be called as an T2G orbitals. And the distance in the splitting of orbitals will be known as an CFSE, which will be known as a crystal field splitting energy or crystal field splitting parameters, and it will be denoted by a delta O, where O will be the significant for an octahedral complex or octahedral geometry, and the center part of the splitting energy will be known as an barymeter. Will be known as a barymeter. And here this EG orbital will be experiencing the higher energy and will be having an energy value of a 3 by 5, which will be equal to the 0.6, and whereas T2G, which will be experiencing the lower repulsion and moving to the lower state, will be having an 2 by 5 of the energy level, which will be equal to the minus 0.4. Why we have taken here minus? Because the electrons which will be approaching these T2G orbitals will be having a lower energy and hence will be considered as a negative values. Clear? So now this is about the crystal field theory in the octahedral geometry. Now based on this concept, we can get a many set of the questions in your competitive exams. So here some of the questions which will be based on this crystal field theory will be asking about their configurations with respect to the electrons which will be filled in the EG and T2G orbitals. And remember one thing, if a strong ligand is approaching a metal ion, then the splitting will be higher. Or the repulsion will be higher. As if weak ligand is approaching the metal ion, then lower will be the repulsion force, or the lower the splitting. Clear? So, next coming to the configurations. Here I will take an example of a strong ligand which will be approaching the metal ion, and here the configuration will be D1. So what happens when the strong ligand is approaching the octahedral geometry of the metal ion? When the strong ligand is approaching, the splitting will be higher and the electrons will enter into the T2G orbital. And remember that here also while filling the electrons, you have to follow the Hund's rule. So here in the D1 configuration, the T2G orbital will be having 1 electron and EG orbital will be having 0 electron. Likewise, in the D2 configuration, the second electron will be filled into the second orbit of the octahedral, second orbit of the T2G, and T2G will get the 2 electrons, still EG will be having 0. For the D3 configuration, the third electron will be entering into the vacant orbit of the T2G, and now T2G will be having 3 electrons and EG will be having 0 electrons. Now for the D4 configuration, here the strong field ligand is approaching. So in the D4 configuration, the fourth electron will be entering into the T2G orbital only. It do not shift to the EG orbital, as if the distance or their splitting will be higher. Clear? So for the D4 configuration, T2G will be having the 4 electrons and EG will be having 0. Likewise, for D5 configuration, you will be having T2G of 5, EG will be 0. D6 will be having and T2G of 6 and EG will be 0. Next, for the D7 configuration, in the T2G orbital, maximum electrons can be filled only with the 6 electrons. So the 7th electron will enter into the EG orbital. Clear? So likewise, for the D8, T2G will be 6 and EG will get 2 electrons. For D9, T2G will be having 6 and EG will get 3. For the D10, T2G will be having 6 electrons and EG will be having 4 electrons. As if in the EG orbital, the maximum electrons can be filled only with the 4 electrons. So this is how the configuration, based on the configuration, and questions can be asked in your competitive exams. Or they might give you the complex, which will be having a strong ligand. For example, if you consider having a platinum, which will be having a CN ligand of the 4. So here they might ask you the question of the D4 configuration for this complex. So what will be the D4 configuration for this such complex under the CFE? So there you have to remember that a strong ligand will be approaching the D4 configuration. You can see the T2G of 4 and EG will be having 0. Likewise, for the weak ligand also, in the weak ligand what happens? The distance, the splitting distance or the splitting energy will be very less, and hence the 4th electron will be filled to the EG orbital. For the weak ligand, D4 configurations will be having an T2G of 3 and EG will be having of 0. So likewise, you can calculate for the other configuration also. Clear? And there is another question which was asked in the NEET examination, which was based on the CFSE value. They were asked about the low spin complex which was having a D5 configuration and what was its CFSE value. So to calculate the CFSE value, there is a formula where CFSE will be calculated as, for in the octahedral complex only, minus 0.4 of the T2G multiplied by the total number of electrons which will be present in the T2G orbital plus the 0.6 into the number of electrons which will be present in the EG orbital. So this will be the equation to calculate the CFSE value, and if there is a presence of a paired electrons, then you will multiply those paired electrons to the equation. So for example, D5 which will be in the low spin complex. Low spin complex in the sense where all the 5 electrons will be filled in the T2G orbital only. Clear? And EG will be having 0 electrons. It doesn't contain any electrons, which because it is a low spin complex. So now if you substitute the values where 0.4 into the total number of electrons in the T2G orbital will be 5 plus 0.6 into the total number of electrons in the EG orbitals are 0 into the number of paired electrons. Number of paired electrons you can find only will be 2 pairs. So by substituting the values and by simplifying or by calculating, you can determine the CFSE of the complex, of the given complex with respect to its configurations. Clear? I hope everyone have understood about the CFT and importance of the CFT for your competitive exams and as well as for the book. Thank you.